my friend and colleague Pablo that speak on geometry of our system of conservation law.
Thank you, Amaury, for the presentation. And in honor to Dan Marchesin 17 Verde, I'm not going to make any bad joke, so I'm going to speak some of the things that we were working together. Many of these ideas maybe were running on my head for the last 6 years, and now I'm going to try to make a walkable path to try to explain you. There are some things that we were thinking about it. Some of those are preliminary results because they are previous to the thing that I really want to talk about it. The first one is not related to the rest, but the second one it is. And maybe the new part is the two next topics, and I'm going to make some relation to a work that we have together with Eduardo, Fred, and Dan. Okay. The first thing that I start to study when I start with conservation laws was secondary bifurcation curve, for example. If you take the Rankine-Hugoniot condition, you know that is a bifurcation at the very beginning of the Rankine-Hugoniot condition, and you can find another singularity. And this can be trackable with algebraic cube theory. And if you take, for example, Corey model, what we call Corey quad, that is when the fractional flow functions are given for the square of the saturations, you can see that this is going to be a third-order polynomial. So when you have a bifurcation curve, you need that this one is a straight line and the other two curves are made by the quadratic polynomial. Things that are interesting is that if you have an umbilic point, then you only can have three lines that intersect at the very point, at the reference point. This result is a little bit related later. That is what we call the boundary extension curve. That is, if you take the saturation triangle and you take one of the edges when one of the saturation is new, you are looking for sonic shocks from the inside of the saturation triangle to the boundary. And this, one of the relations is that the speed must be given by the eigenvalue. This must be S because it's the eigenvalue. It's an S, I don't know. And this is what the engineers call it the interstitial velocity. One of the relations is direct, the other direction is difficult, but if you have an S-shaped fractional flow in the border, you can do it directly. This is just two remindings. Now is what I really want to talk about it. I'm going fast with these ones because nobody wants to lose the lunch. So this is the idea. Everybody knows Oleinik criterion. If you have a scalar flux, for example, this quadratic, and you have the left state here and the right state here, you have to take the convex hull from here to here, so you are going to have a line, and from that you have a shock wave. And the speed of the shock is given by the inclination of this line. If you do it in the other way, then you have the left state here and the right state here. The convex hull is going to give you this curve, and from this you are going to calculate the rarefaction and the speed. What we see is that these things start to move on time. Here is a line because I'm setting here also the time, so I can see the speed of the shock, how it's going to evolve, and here we have the rarefaction. A little bit more and a little bit more, and it's always going to have this self-similarity wave to do it. But what is interesting here is what is beneath. That is what really the relations that we are seeing. Rankine-Hugoniot conditions give us these two the speed of the shock velocity, and here is a little hidden the speed, but the speed at the end points is given just by the derivative of the flux in the 2 points. And you need to calculate how is going to be the profile by inverting this parameter that is going to give you the speed of the rarefaction wave. So these two ideas are very important in a way that we can use it to try to formulate these kind of things in a more general profile. For example, if I have a flux, any kind of flux, and this is my left state and this is my right state, so Oleinik tell me that I need to take the convex hull of this, of the old profile with the original flux. The shocks are going to be given by these dotted lines. Rarefactions are going to be the small parts where the two functions are together, the original flux and the convex hull. And okay, I can calculate this. So if I derivate the flux function, I have this function, and if I derivate the convex hull, I have this profile here. This is what Oleinik says that we need to do it. And the idea is that maybe we can reflect this curve and have this. If you see, I have a rectangle here is A, B, C, D, and here I have A, B, C, D. So the straight lines were shocks and are going to be now vertical lines. The small part of the rarefaction are going to change, and this is what Oleinik said when we have the scalar flux. So now I have this profile and I can do the evolution in the solution here, and it's the same like before. This idea is very easy, and the idea is how to translate that to systems of conservation laws. So I want to try to make what I call the effective flux function. Maybe the name is not the right one. So I want to make in phase space a base curve that is going to control where are the saturations or phase states that are going to be related to the wave that I'm looking. And I'm going to, after I have this base curve, I'm going to make a lifting of that curve, and I'm going to get what I call the effective flux function. And this lifting is the most important part for me. So when I have a shock curve, I can use Rankine-Ogonio conditions, and I can use this condition to try to find all these phase points that are going to be there. And for the rarefactions, it's easier because I have where exactly the integral curves passes through the phase space. So I'm going to take these two ideas and try to do the lifting. This is the first lemma. This one we use it actually very well before without noting this, but it's the same. Okay, now assume that I have a reference point that is R in phase space, and I can construct the Ogonio locus. From the Ogonio locus, then I can reparameterize the Ogonio locus, for example, in this way. Every U is going to be in the Ogonio locus, and I'm going to call it, for example, the first coordinate is going to be my coordinate that is going to parameterize that curve. And the second one, okay, I can find it because I have the locus. I know that this locus is going to be useful before I reach a Bethe-Wendorf point, when one of the characteristic speeds is going to be the same as the speed of the shock wave. So I'm going to take my base curve is going to be just the Ogonio locus. And what is going to be the lifting? The lifting, what I'm going to take is when L is the reference point, I need that this one will be the same height of the elected function. So here I elect the first coordinate to try to parameterize the curve. So I'm going to take the first flux of the conservation laws. And this is exactly the speed velocity from the reference point to the point in the state space. If you see, this is going to be from an interval to the reals. So this is a function from 1D to 1D, and not more a function from 2D to DD. Why this is working? Okay, if I take now the scalar shock speed from any 2 points in this curve, given for the base curve is going to be the same as the speed that I use for the Rankine orthogonal condition in the system for two conservation laws. So I can say that the effective flux function is exactly the first flux restricted to that base curve. This is easy to do it. We did it before and there is no problem. The problem is when we try to join a rarefaction curve there. But it's exactly the same. If I have now the reference point and I'm going to construct a k-integral curve, you can think one of the families that you have in your system, then for any state in that Rankine, in that rarefaction curve, I can reparameterize it with one of the coordinates, and the problem is how to do now the lifting. And this is the part that takes some time to do it. And the lifting is more or less the same. At the reference, I need to be at the height of the reference, and now I'm going to integrate just the eigenvalue that I'm using to have this condition. When I derivate the effective flux function, I'm going to have the speed that I'm looking for. One thing that is important is that if I take the gradient of the base curve, because this is an integral curve in the phase space, then the vector that is only derivating the base curve is going to be parallel to the eigenvector, to the respective eigenvector. And this is going to give me what I need. That is that if I derivate the first flux along the base curve, this is only the chain rule, but at the right I can guarantee that this is exactly the same value as the eigenvalue. Because if you see, this is the first row of the Jacobian matrix, and as I said, this vector is parallel to the eigenvector. So this relation holds, and like the first coordinate of this vector is 1, this relation holds. And this gives me the same idea that I have with the shocks. The effective flux function, I can use it like the first flux restricted to that curve. So what I need is to have this base curve, and this base curve is going to be only one of the wave curves that we use. So this is my theorem. The thing is that if you have a wave curve in the phase space, you can use it with any of the fluxes that you want, and it's going to be your effective flux function that you can use it to try to see the Oleinik criterion. Of course, I can use any of the coordinates of the system to do this. Even I can use a convex combination of the coordinates. What did I write here? One of the things that I think that is nice is that this is admitting the Liu criterion for admissibility. And there are some things that are important. If you concatenate two wave curves, one of the slow family and one of the fast family, then the intermediate state is going to be created naturally. But for example, for transitional waves, you are not going to see it because I'm losing the information of which wave I'm using. If the slow one, the fast one, I don't know. Just let me give you some examples trying to resume what I said. I'm using a convex Corey model. This means that the mobilities, this is not the mobilities, sorry, this is the mobilities, because we have viscosity, 2 viscosity for oil, 1/2 of viscosity for gas, and 1 for water. This is what we call the universal structure for wax solutions. Here I have the saturation of oil, this is the saturation of water, this is pure water, pure oil, and this is pure gas. We are going to, our left state is in the gas-water saturation, and our right state is pure oil. We know that there is an optimal solution that is given by a rarefaction joined to a characteristic shock to oil. And here I'm do a little trick, because if we are with a little higher of water saturation, then this shock is going to reach a shock is going to reach a state in the water-oil side, and then it's going to continue with another shock. This is the solution profile, water saturation. This is the wave that I'm looking, the set of waves that I'm looking. I have a rarefaction with the water saturation decreasing, and the gas saturation is going to be only this part is only decreasing. The rest is oil saturation, and I have this strong shock that is going to be the displacing wave. If you want to see it only by oil saturation, you add gas and water and subtract from one, and you see that this is going to be the rarefaction, and the displacing wave is going to be all this shock. This is what we've done before, and this is what I'm saying now. Now I'm going to take the effective flux function that is only take the fractional flow of oil in oil saturation, and I'm going to make the lift of this path, and what I get is this is the part of the rarefaction. Here I have a small shock, and here I have the other part of this flux function here. So if I do this idea of taking the convex hull and derivating, I'm going to see that this is going to be just the rarefaction that I'm dividing, and this is the shock from here to here. Actually, there is a small step here that is almost unseen. You cannot see it because the speed is more or less the same. If I do the reflected part of this, I'm going to have the same solution that I had before. The same can be done with a lower saturation of water, and the shock is going to be given in the other side, and I have the same solution. But this is, I can do any kind of injection. For example, what happens if I take this saturation? Then I know that the solution is given by rarefaction, a shock wave to the boundary, and here I have a small rarefaction and another shock wave to the oil. So when I take the effective flux function, I see a rarefaction here. There is a small shock over here that is, I didn't know that is going not to be seenable. Here is a small rarefaction up to here and another shock to here. So when I derivate the convex flux function, I see the rarefaction. Here I have the shock wave, and here in a vertical I have the intermediate state that appears naturally in this configuration. So when I reflect it, I get exactly the same thing that before. So this is a good idea to try to at least draw the profiles from solutions. Here's another thing that maybe what Sido, I don't know where Sido is, and many others have called the banana theorem, is because you can see this triple shock rule from shocks from here to here to here. They are the same speed from a shock from here to here. And this is the two effective flux functions that I draw before, and I only continuated with the things in the boundaries, and you see that all these states have the same velocity. Okay, this is more or less what I want to say, and go for concluding some further work. Fred had a conjecture that maybe now is provable, that when you go to a boundary extension because of the sonic shock, you must pass through an inflection manifold. This is more or less, I think that this can be a way to try to prove this kind of conjectures. This is one of the problems that we have, is that I still need the wave curve method to try to construct the wave groups in the phase space. So, this is this point, sorry. The Goniolog is easy because it's just this algebraic curve that is easy to calculate, but the integral curves are difficult, and maybe Amaury has a very good idea how to do this with a Hamiltonian approach. Another thing that is, maybe this is one of the things that is interesting for me, is that if we have some experimental data where we can see how are the profiles of the injection, we can extract the flux function from this, because it's to do the reverse order of what I have done here. Of course, there is problems here. The profile is only with one of the saturations, for example. You need maybe another of the flux functions to try to do the other profiles for the other saturations. And of course, if you try to do the experimental data, I only see the things when we have rarefactions, because we can measure the speed of every point in the rarefaction. But the shock wave is only going to connect me one point to the other point in the state space. Everything that is in the middle, I cannot take it. And one thing that I don't know if this could be great is maybe we can try to find some shock admissibility criterion when we have, for example, non-local branches of the Huguenot locus. This one I'm going to tell you later how I'm thinking about it then. And okay, that's all. And feliz cumpleaños, Dan. And thank you for everything. Crystal clear. No, everybody needs to go at lunch, so thank you very much.